Hey guys, in this video we're going to be talking about gas density, molecular weights of gases. We're going to look at stoichiometry calculations involving gases, all in this one video. So, if we think about a gas, we can look at 1 mole of gas at standard temperature and pressures. At standard temperature and pressure. We call this gas at standard temperature and pressure STP, so that's how I'll refer to it from now on to speed things up a little bit. If we have any ideal gas, then 1 mole of a gas at standard temperature and pressure will always occupy a volume of 22.4 liters. So no matter what type of gas it happens to be, helium, neon, nitrogen, ammonia, whatever. If you have an ideal gas and we are at standard temperature and pressure, it will equal 22.4. And if you're not sure, if you think I'm full of it, you can put this into your gas law. And you can put your 1 mole in, your pressure of 1 atmosphere, your temperature of 273.2 degrees or 2 Kelvin, and put in your gas constant, and you'll find that you get a value of 22.4. Now, this is always true. If you have a standard temperature pressure gas that is ideal, 1 mole will equal 22.4 liters. So you could say that 1 mole is equal to 22.4 liters at STP. So it can be used at it as a unit conversion, right? Now, what does change is our density. Density is based on mass, and masses of gases are going to change. So if we think about helium versus N2, N2 has a molar mass, or molecular weight, equal to 28.013 grams per mole, while helium has a molecular weight of 4.003 grams per mole. So because they're occupying the same volume, helium will have a much lower density than nitrogen will. Okay, and we can determine our densities pretty easily. Let's go ahead and solve for densities of gases. So let's try one where we're trying for the density of methane. So let's look for our density of methane. Density we show as rho, that weird funky little p thing. So we want to solve for our density of methane when we have a pressure equal to 910 torr and a temperature equal to 255 Kelvin. We don't necessarily have to find the density at STP. We can though if we would like. We would just put in 760 millimeters of mercury or 760 torr or whatever. So let's go ahead and convert this from torr into atmosphere so we can use it into our ideal gas law. So we have 760 torr per 1 atmosphere, giving us 1.2 atmospheres. And then we're going to basically put all this into PV equals nRT. So our pressure, 1.2 atmospheres. We're trying to find density, so we don't know volume or moles yet, and that's okay. So leave those be for the moment. But we solve for everything else. Okay, and what we want to solve for here are moles over volume, because that's going to get us to some amount per volume. And when we solve for that, we get 0.05722 moles per liter. We can then convert our moles into grams using our molar mass. So we have 0.05722 moles of methane per liter. Our methane has a molar mass of 16.043 grams per mole. And we get 0.918 grams of methane per liter. We can then, if we want, put this into a density like we normally see. Where we convert this into milliliters, grams per milliliter, which would be 9.18 times 10 to the negative 4 grams per milliliter. It's a very, very small value because it's a gas, not very dense. Next thing and last thing in here we're going to look at is gas stoichiometry. So adding stoichiometry component to our gas law, or adding our gas law into stoichiometry, whatever you want to call it. So gas stoichiometry, we bring the ideal gas law in to a stoichiometry problem. So I feel like the easiest way to kind of look at this is just to do an example. So we should know how to do stoichiometry. What we're trying to get to in stoichiometry is moles. So trying to get to moles, almost always. So let's try. So we have acetylene gas, C2H2, and it's going to undergo combustion. When it's combusted, it's going to produce carbon dioxide and water, right? So we have C2H2 plus O2 goes to CO2 plus H2O. When we balance this out, we get that right there. So when we combust acetylene with oxygen, we produce carbon dioxide and water, and we want to know how many liters of C2H2 are required to produce 75.0 liters of CO2 at standard temperature and pressure. And we also want to know what volume of H2O is produced and what volume of O2 is required. And all of this is going to be at standard temperature and pressure. So the first thing we need to do is we need to go from liters of CO2 into moles of CO2 using, well, in this case, we're at standard temperature pressure. So remember that 1 mole of any gas is equal to 22.4 liters. So we can go ahead and bring that in. So we have 75.0 liters of CO2. 1 mole of CO2 has a volume of 22.4 liters, giving us 3.35 moles of CO2. We can then take that moles of CO2 and use regular stoichiometry. So we have 3.35 moles of CO2. We're going to use a mole-to-mole ratio to go from moles of CO2 into moles of acetylene, then moles of water, and moles of O2. So 4 moles of CO2 are produced by the combustion of 2 moles of acetylene. So when we do this out, we get 1.67 moles of C2H2. And now that we have our moles of C2H2, we can convert that into liters using 1 mole of acetylene has a volume of 22.4 liters. Giving us 37.5 liters of acetylene required. Next, we can start back at our 3.35 moles of CO2. For every 4 moles of CO2, we produce 2 moles of H2O as well. All right. And I'm just going to go ahead and convert 1 mole H2O, 22.4 liters. Gives us 37.52, or 37.5 liters of H2O, which makes sense because we have the same number of moles of C2H2 as we do H2O. Lastly, let's take our 3.35 moles of CO2, convert that into moles of oxygen. So we have 5 moles of oxygen for every 4 moles of CO2. And then using our 22.4 liters per 1 mole of O2. Gives us 93.8 liters. That is how you do gas stoichiometry problems. Quick and easy. Okay, guys, that's everything for this video. Bye.